Hello, we have done the load shear bending diagram for 2 examples using graphic approach. Today we're going to look at our third example. So load shear bending diagram using graphic approach. Example 3. So this is going to be the same example we did for analytical approach, but using graphical instead. So taking out that beam, we have a concentrated moment here, 80 kilonewton meter. Then we also have distributed load at the second half of the beam, 5 kilonewton per meter. Then in addition to that, we have a concentrated load, 15 kilonewton right here. Then the beam dimension is 5 meters on each side. Okay. We also, using our entire FBD, we calculated the reaction support at A is 5.75. At point B, we calculate it's 34.25 kilonewton. So directly jump into our graphic approach. That's I'm going to borrow this one for our load diagram. So that's basically our load. And we're about to draw our shear. Then this is going to be our bending diagram. Okay. So shear. For this one, rule number 1 in the graphic approach, when you have a force, external concentrated load going upward, the shear gonna go the same direction, so which means gonna jump up at the beginning to 5.75 kilonewton because this is going upward. Then we're going to smooth sailing because there's nothing going on, there's no other forces. You might be wondering, we never talk about 80 kilonewton meter. That's true. Remember the last example we're talking about, this is a moment. Moment does not affect shear. Moment only affects our bending diagram here. So we don't worry about this 80 kilonewton in the shear. So when we have a stay constant until at this midpoint we encounter this concentrated load 15 kilonewton first, and it's going downward, so it's from 5.75 downward 15. So what would be 5.75 minus 15? That would give us negative 9.25. So that's where this value will be. Then we have encountered a new thing now. We're going to continue to move. What do we see? We see this distributed load. How do we cope with distributed load in graphic approach? Let's go back to our rule. We're going to go back to using this rule. Distributed load. If we have a distributed load, we have this rule. The slope of the shear is going to give us the intensity. In other words, I'm going to write down using integration method, which means if I were to integrate your intensity, the distributed load intensity, that will give us the shear. Okay, so keep that in mind. What's our omega? That's our intensity, 5 kilonewton per meter. So in other words, if we were trying to integrate this intensity, omega, we're going to give us shear, which means the area underneath this distributed load, this green, yellow highlight is gonna translate to the shear. So we're gonna calculate what's the area underneath this distributed load, and it's 5 kilonewton for this dimension, and the length is 5 meter. Okay, that gives us 25. However, is this 25 positive or negative? We have to go back to see our rule. So the rule really didn't see it. And here I needed to add that information to this rule number 2. So if this is going downward, let's go ahead and just add it in. If this distributed load is downward, then we're going to minus, okay? If it's going upward, we're gonna add it. We don't normally often see any distributed load is hoisting the beam. It's pretty much all adding on it, because in reality you have, beam, it's supported, it's have to support all those weight of the roof, the snow, etc. So all those are snow load or roof weight, all those are downward force. So in that situation, we have this area as negative value because it's going downward. So now we're going to go back to our shear diagram. That's where we stopped here when we're talking about distributed load. If you were trying to integrate this entire area here, you will minus 25 at the last point, right? Because when you so you start with negative 9.25 and then you integrate this entire area, which means negative 9.25 starting point minus this 25, that will give us negative 34.25. And be aware, this shear is integration of the omega intensity. And this omega is a straight line. It's a constant value. It's 5 kilonewton. Well, again, using the same concept, if y is a constant, then integration of this y is going to give us power of 1. In other words, this is going to be linear. And then when you have negative 34.25, don't forget there is a concentrated load going upward. Rule number 1 in the graphical approach. If it's going upward, you're going to go the same direction, go upward. So from negative 34.25 upwards 34.25 going to get us land to 0. So that's our shear. Okay. All right. So the last thing we're going to worry about is bending. So far, you already know bending is basically integration of the shear. You are going to integrate that, correct? So we're going to integrate. But before we integrate, don't forget this problem. Initially, start with 80 kilonewton meter. That's a moment. So we have to incorporate that value into your bending diagram. This is a clockwise rotation, last rule in our graphic approach. If it's clockwise rotation, we're going to jump upward. So we're going to start at 80 kilonewton meter. Then we're going to integrate your shear to our bending. And this area is above, so it's positive. And if you were to integrate this entire rectangle, that will give us the area of 5.75 for this dimension and this dimension is 5. So that will give us the value of 28.75. Okay. So what does that mean? If we were to integrate this entire area, we're going to add value until from 80 plus 28.75 will be this value. So this value is going to be 80. That's our starting point, plus 28.75. That will give us a value of 108.75. That's the end value for that point. Okay, so we know the initial point and we know the final point. The rest is connecting the dot, right? But don't assume every single problem is going to be a linear line. Some of them can be power of 2. Parabola sometimes can be cubic curve, power of 3. For this particular case, what would be? Because this is a straight horizontal line, it's a constant. When you integrate a constant, we have a power of 1. So for this case, we can draw. It's just a linear line. Okay. Then we're going to move along. We're going to look at integrate the second half of our share. Then this area is below. So this area will be negative value. And this area is a trapezoid shape. And we're going to figure out the area. So if we were trying to decompose to rectangle and the triangle, so this rectangle will be what's our length here? That's our 5. And what's our height? Our height is this value, right? 9.25. Then that would give us negative 46.25. Then we're going to calculate the area of this triangle. We did this rectangle. Area of this triangle, the length here is again 5 meters long. And what's the height here? Remember this point we have, it's this value. And this point is negative 9.25. So the length, the height over here will be 25. Okay, so it will be times 25. That will give us, divide by 2 because it's a triangle, half base times the height. That will give us of 125 divided by 2, that would be 62.5. Again, this will be negative value because it's below the axis. Okay, so we're going to add both of them together to give us a total value, a total. So when you add those two together, negative 46.25 plus negative 62.5, and we will have negative 108.75. Okay, so what does this value mean? Which means if you were trying to integrate this entire trapezoid, you're gonna minus this much value when you get to this point, the final point, right? So where do we start with? We start at here. We start at 108.75. This is our peak value. Then we're going to add negative 108.75. That gonna brings us down to 0. So how do we get this 0? It's 108.75 from this point. Gonna be integrate plus this entire area, negative 108.75. That give us 0. Okay, so you know the end point, you know the initial point. How do we connect those two dots? This is no longer a linear line, right? This time. Because why? You integrate this line here. And this line already is part of 1. Y equal to some slope times x. We don't care about the slope at this point because it's just, when you integrate, you're going to get power of 2. So when you get power of 2, you're going to get a parabola shape. So you can either get parabola kind of like that shape, curved that way, or that way. So which one will be correct? How do we verify it? So here we're going to go back to our rule. Let's go back to our rule number 3 here. Rule number 3 states the slope of the bending is going to be equal to shear. So we're going to use that to help guide us. The slope of the bending at this point, the slope, that's going to be equal to the shear at that point. What's the shear at this point? It's negative 9.25. So if we were trying to draw a curve this way, right? That means or verse this way. Which one would be better? Now let's continue to investigate. At this point, the last point right here, what's going to be the slope here? The slope here gonna be equal to the shear at that point. The shear at that point is equal to negative 34.25. Okay. So which means the slope from negative 2.5 to negative 34.25. So the slope is actually decreasing, right? It's like a higher magnitude. So if you think about this one, if we were using this curve, the slope is here at the beginning and its slope is decreasing. So if we were using this slope, this curve, it shows the slope is actually drop really quickly at the beginning and then drop slowly at the end. It's not what we have because the slope here, it's actually 9.25 and then here it's 34.25, right? So what that tells us is going to curve in this direction. So this would be correct because over here the slope is negative 9.25 and here you drop even quicker, it's 34.25. In that situation, we can go ahead to erase this possibility. That's how we eliminate that possibility, knowing how the curve is curved up or curved down this way. Okay. So that gave us our bending diagram for this one. A lot of calculation in terms of area and a lot of graphical rule embedded to it. So go ahead and review this and try some problems yourself and go exploring it. So happy exploring. See you next time. Bye.